All right, so this is section 6.2, part 3. We're still working on volumes. So last time we'd looked at another revolution, surface of revolution, where the volume of revolution, where the cross sections were circles, and then we also saw one where cross sections were washers. So let's do another example where we get washers. And it's a little different here. So we want to find the volume of the solid obtained by rotating so the same region as the last one, the region bounded by y equals x and y is equal to x squared about the line y is equal to 2. So last time we rotated about the x-axis. This time we're going to rotate it about the line y equals 2. So what that's going to look like. So I'm going to draw this again. I'm going to modify how I'm drawing this so I get a better picture. So what this looked like was I had something that looked like this. And now I'm looking at the line y equals 2 here. I'm going to take this thing and revolve it around, and what that's going to look like. And again, art skills are not the best. I'm going to get, another cone-looking thing here, except it's not going to close exactly. So inside here, let's see, have something that looks like this. And then again, this is revolved around. So again, I have washers here. If I look at a cross section, my cross-sectional area are these washers, and we talked about how to find those areas. I'm still going to determine what the x values are for my integration, and we did that last time. We know that this goes between 0 and 1 here, but now the problem is I need to figure out what my big radius and my little radius are. I need to figure out what this distance is and what this distance is. Okay. So one thing you'll notice is, if I look at this, if I look at, how I want to write this. Yeah, so if I look at how I want to write this, you'll notice that, this line right here, so this curved one is the line y equals x squared. Actually, yeah, so let me fix this drawing because I did mess up on that. So this is going to go like this, and then like that. So let's, yeah, so I have those backwards all around. Let me fix these. So this is the straight line. This is the curved one. Okay. So let's use these two down here at the bottom to figure out what the radii are. So you'll notice if I want to get, this distance here, I already know that this is up a distance y. So we called it y1 last time. We'll call this y2, and then y1, y2. So I know this is up a distance y, but if I want to figure out, so I want to figure out what this distance is. So you can imagine, I have, whatever the distance from here to here is, and then I subtract off that distance. And that'll give me the that height there, that y1, or that this one right here. So what I'm going to do for this one is, so what I do is I just take 2 minus y1 for the radius 1 and 2 minus y2 for radius 2. So let's go back and look at the picture, make sure we understand that. So let me erase these, make things a little clearer. What I want to find, so this graph is a graph of y1. What I want to find is this distance here, because that's the distance of my inner circle. So to do that, I know that this distance here is 2. And so if I take 2 and subtract off y1, that'll give me this distance here. And I can do the same thing for y2. It's the exact same thing. So I'm going to go ahead and do that. So r1, so the radius, so that's going to be the inner radius in this case. R1 is going to be 2 minus x. Yeah, 2 minus x, where that's down to the straight line, and R2 is going to be 2 minus x squared. So now if I want to figure out the volume here, I'm again just going to integrate the area of that washer, dx still, and that is going to be the area of this washer from 0 to 1 is going to be the pi times the larger radius squared. So this is going to be R2 squared. R2 is the larger radius minus R1 squared dx. Okay, so when I plug this in, this is pi times the integral from 0 to 1. R2 squared is 2 minus x squared minus R1 squared, which is 2 minus x squared. So now I just go through and finish the integral. So 4 minus 2x squared, sorry, 4 minus 4x squared plus x to the fourth minus 4 minus 4x plus x squared dx. So I'm going to leave the integration up to you, simplifying that, but when you do, you're going to get 8 pi over 15. It's more about the setup. So again, this one was different in the fact that we were revolving around you know, an axis. So when that happens, when I'm revolving around an axis that isn't the x-axis or the y-axis, so typically it's going to be like x equals something or y equals something. So let's say x equals to a. Then the way that I get my radii is I'm going to do a minus the y value is going to be my radius. That's pretty general. Okay. Oh, okay, so let's do another example. So I think this is going to be, yeah, so this will be the last example, second to last example. Okay. So this is another example. So find, we're going to beat this one to death, the volume of the solid obtained by revolving y is equal to x and y is equal to x squared. About the line x equals -1. Okay, so just real quick, I'm gonna erase this for now. I need to think about it for a second. It's getting late while I'm recording this, and I don't want to write down anything that might be wrong. So let's ignore that stuff up there, and I'm going to finish out this this example and then probably upload this. Okay, so I'm going to draw this. So same idea. In fact, same region here. So I have that. Now I want to revolve around the line x equals -1. So I'm going to get something that looks like this. Okay, and again, I'm going to use washers, but now my cross sections are this one, so I need to figure out, what this radius is and what this radius is in order to do this. And I'm going to integrate, since I'm integrating up and down, it's going to be an integral dy this time. So if I look at, so let's erase those so we can see what's happening. So my straight line here is the function y equals x, and if I want to figure out what this distance is, so I'm interested in what the radius is. So it's going to be, I know this distance from here to here is, so I know this distance from here to here is 1. I know this distance from here to here is x. So the radius, the inner radius, and I'm going to start calling it that because that makes a little more sense. The inner radius here is going to be 1 plus x. Let's call it x1. So it's 1 plus x, the x distance to here. And then for the outer radius, so sorry, it's not x1, it's just x. That's going to be 1 plus, that's going to be 1 plus x. I'm going to call this outer. I'm going to call this x inner. You'll see why I'm doing that in a second. Sorry, that's what I was taking so long to do. I need to distinguish these. So the inner x value, which is given by y equals x, this is just 1 plus x. For the outer one, this is a little more difficult. So I need to put it in terms of y. So when I do that, I'm going to get 1 plus the square root of y. So x outer is given by, if I solve this equation for x, so it's x is the square root of y. And because I'm integrating in terms of y, I need these things to be in terms of y anyway. And now 1 plus x is just 1 plus y because y is equal to x there. So I'll put everything in terms of y, and now I'm just going to do my integral 0 to 1. Pi times the outer radius here is 1 plus square root of y squared minus the inner 1 plus y squared dy. And then this integral is doable. I'm just going to write the answer just for the sake of time. You can go through and do this. This one ends up being pi over 2. So I'm going to stop this one here because my explanation quality is obviously decreasing. I will upload one more page of examples of these. That way you see a few more of these so that it makes sense. You get some practice with it. So I'm going to stop now.